5-year-old, 10-year-old version of OneNote and see what happens. Okay, so
What a turnout.
my mind is blown this semester. Okay, so the spot where we ended on Thursday was dealing with limits that we normally could deal with in other ways, but the interesting / fun thing is that you can just replace a function with its power series as long as the place where you're evaluating the limit at is in the interval of convergence. And so this limit is as x goes to 1, 1 is in that interval of convergence. So we can evaluate this limit using power series instead of traditional methods. Obviously using like a traditional method here, like L'Hopital's rule, is going to be faster. This is just sort of to illustrate that we can replace, anytime we are doing math on a function, we can replace that function with its power series and the math will still work. So these aren't hard. Oh gosh, this doesn't even have the pens when I go to full screen. Oh my gosh. Okay, so we have to go up to here and use this pen. Okay, so let's go ahead and see what we can do here. So we'll replace, can I make that a little, I don't even remember how to control the thickness on those. Okay, so we're just going to replace the natural log of x with this power series that it's equal to. So we're going to put this into the denominator, and then we're going to simplify and evaluate. Man, this old version has really kind of mediocre, where's the eraser now? There. Has really mediocre inking. Oh boy. All right. Wait, didn't I go back to pen? Okay. So we're just going to replace the function with its power series. And what we notice is that there's an x minus 1 that's common to all the terms in the denominator. And so what we're going to do is cancel a factor of x minus 1 out through, we're going to cancel it throughout everything. So x minus 1 goes into the numerator once. So we're dividing both the top and the bottom by x minus 1, which again is basically multiplying by 1. And when we divide the first term in the denominator by x minus 1, we get 1. When we divide the second term by x minus 1, we'll end up with x minus 1 over 2. When we divide the third term, we'll end up with x minus 1 squared divided by 3, etc. And this limit can now be evaluated. We're taking the limit at 1, and what we are going to see is that all of the terms to the right of the first term, all these are going to go to 0 as x goes to 1. So we have two terms that aren't going to 0. Those are the numerator and the denominator. Okay, back to black. So that limit will be 1. So the key, the algebra is not too hard. We just have to make sure you know your power series. So there's 5 that you need to know for exam 3. Well, I'll write them on the board again, but you have to know those the 5 you need to know so that you can do this substitution. So down here we have the limit as x goes to infinity of this expression. And what we're going to do is replace e to the 1 over x with its power series. We have the power series for e to the x right here. We're going to replace the e to the x. We're going to replace this x with 1 over x to get the power series for e to the 1 over x. So every x that we see is going to become a 1 over x. So this is going to, the effect of this is that we are going to be pushing powers of x into the denominator. And then there's a subtraction of 1 here. So it looks like that. So e to the 1 over x, we find its power series by replacing x with 1 over x. Substitute it in. We notice that there's some cancellation here. So this 1 right here is going to cancel with that negative 1. And now we're going to distribute. I wonder if I can pin that. That might help. Okay, helps a little. Then we can distribute this multiplicative x right there across. And when we do that distribution, we'll end up with the limit as x goes to infinity of 1 plus. So 1 factor of x is going to cancel in each of these fractions as we go out into the tail. And as x goes to infinity, this limit is 1, because each of these will cancel. Each of these is going to go to 0. So our overall limit is, in fact, going to be 1. So as long as you know the power series, it's not too crazy. Any questions on that substitution?
What are the 5 power series we need to know?
I'm going to write it down again on the board. I wrote it down last class. I'll write it down again. It's in the review. We'll get there. We have 2 slides to finish, and then we'll get there.
Okay.
Yeah.
So we're replacing the e to the 1 over x.
Mm-hmm.
We're replacing the x with the power series of e.
Mm-hmm.
Okay.
So to get the power series for e to the 1 over x, we take the power series for e to the x, and we replace that x with the 1 over x,
Okay.
which means replace every x that we see with the 1 over x. And when you have a 1 over x plugged in here, that becomes a 1 over x squared, so it pushes the power into the denominator. Right.
Okay.
So when you replace that x with 1 over x, it becomes 1 over x cubed, which means x cubed in the bottom. That make sense? No, all the x's are in the denominator, all the remaining x's after we do this distribution. So this is the only term that's not going to go to 0 as x goes to infinity. All right, let's take a look at a couple of approximations. So we have a definite integral here. We have a binomial that you normally have no clue how to integrate. Right? You don't know how to integrate that with any technique we've used so far. You could try to do a trig sub and see if there's some backdoor way you could get to it, but there's no obvious way. And we want to do this approximation so that we have an accuracy or an error to be less than 10 to the negative 5. And what we are going to, well, we'll see a couple things, but let's first start it. So we're going to replace the function on the inside with its power series. So this is the binomial series, the BS, as opposed to the GS for geometric series. So the binomial series is right there. Now we have an x in here, but we have an x to the 4th there, so we're going to replace that x with
X to the 4th.
x to the 4th. So we're going to come over here to the power series for 1 plus x to the half and replace all the x's with x to the 4th. So we're going to end up with, 1 plus, so all these x's get replaced with x to the 4, so that's 1 plus x to the 4 divided by 2 minus x to the 8 divided by 8 plus x to the 12 divided by 16 minus etc. dx. Okay, now we know how to integrate that. That we can integrate easily. It's a polynomial. So we integrate term by term, which is why power series are so nice, because they are basically polynomials. We just integrate term by term. I don't know what 13 times 16 is. Hopefully we don't need it. So we have that, and this is a definite integral from 0 to 0.2. Notice that this interval is within our interval of convergence, so it's legit. Let me move this to... Doesn't like that. Let's see, do I have to lasso it? Weird. Okay, so now let's substitute in. Plugging in the 0 is not going to contribute anything. So all we're doing is plugging in 0.2. So we're going to end up with 0.2 plus 0.2 to the 5th divided by 10 minus 0.2 to the 9 divided by 72 plus 0.2 to the 13 divided by whatever 13 times 16 is, etc. So we have that. This is an alternating series. And we know how to estimate with alternating series. So let's go to Desmos. So we know how to do alternating series. With alternating series, we look at the first unused term. So our goal here is to have an error less than 10 to the negative 5. So we want to figure out what term is less than 10 to the negative 5. So if we plug in, let's try 0.2 to the 5th first. 0.2 to the 5th, is that less than 10 to the negative 5? So if we look at 10 to the negative 5, it's easier to compare it that way. So we need to be less than that, we're not. So then let's go it's 0.2 to the negative, it's 0.2 to the 5 divided by 10 actually, right? Is that less than that? 1, 2, 3, 4 decimals, 1, 2, nope, not quite. So most likely it's going to be this term, 0.2 to the 9, divided by 72, just for good measure. Clearly, when we move that 9 decimal places over, way over there, that's going to be less than this, 10 to the negative 5. So that's our first term that's less than 10 to the negative 5, right here. So this term is less than 10 to the negative 5. So that means that we want to add these. This will be our approximation. So we're going to come over and we're just going to add those two numbers together. So 0.2 plus that one. So it's that one plus 0.2. So there is our approximation. Kind of a big rectangle, but that's okay. Guess I didn't need the whole thing. That's too big. Too big. Let's go back. All we really need is that answer. So let's grab that answer. All right, so alternating series, we just look at the first unused term, and that approximates the addition of everything in front of it. So that's our first term under 10 to the negative 5, so that's our approximation. Don't have to go out very far. So this is what the calculator is doing.
Jim?
Yeah?
I think the arrows next to the highlighters, I think that might be how to change the,
This guy here?
yeah.
Oh yeah, that is good call.
Yep.
So then I can change the thickness here? Or is that, what's that gonna do? Oh, that'll be a little easier, thank you. Oh, I guess it's just gonna grab these whole rows if I grab that. Okay, so if I want black, I need that one. And then, oh, interesting. All right, I'll figure that out. All right, yeah, thanks. Okay, so I'll call them right out during my break and get rid of this version of OneNote. Have them update. It's like, oh my gosh. Really? Okay, so let's try this one. So we want to integrate inverse tan. That's not one that has an immediate antiderivative, but we actually know how to do this. We did learn how to integrate arctan using integration by parts. You could do that. But we're going to use power series this time, and we just want an approximation. So let's do that. Oh gosh, that's too big. I want that one. Okay, so we're going to integrate from 0 to 0.5, 0 to 0.35. We're going to replace inverse tangent with its power series. Oh yeah, that's better inking there for sure. And we notice that the interval that we're integrating on falls within our interval of convergence, so everything is legit. And it's a polynomial, so we integrate term by term. And when we integrate term by term, we will have this. And we're going from 0 to 0.35. Once again, plugging in 0 is not going to be a contributor, so we'll end up with 0.35 squared over 2 minus 0.35 to the 4th over 12, etc.
Don't we also have to change the interval of convergence for these?
Nope.
No?
So inverse tangent of x, that is the interval of convergence. This interval is within it, so we're allowed to replace this with that. We're not adjusting the function at all.
Okay, that makes sense.
Now, what we did here, when we replaced, it's true, when we replace this x with x to the 4th, we have to replace this x with x to the 4th, but it's going to be the same interval of convergence. We've seen that if you replace x with an even power,
Because the fourth root of,
it's going to be 4th root of 1 is 1, so it's not going to change the radius at all.
Right, makes
But
sense.
yeah, so if we're doing a true substitution, yeah, for sure. Okay, so now we have to figure out the first term that's less than 10 to the negative 5. So we'll do the same type of thing. We will figure out, let's see, let's get rid of these other ones. So 0.35, raise that to the 4th power. That's not less than 10 to the negative 5. 0.35 to the 6 divided by, I guess I didn't divide the other one. That, I can't even count the decimal places on there, so I've got to do this. So we've got 4, 1, 2, 3, 4, so it's still not less yet. So it looks like it's going to be the 0.35 raised to the 8th power, all divided by 56.
Yes.
And that's definitely, we have 5 zeros there, so yeah, that's less. So that 8th power, that's the first term under 10 to the negative 8. So let's go with red. So that one is less than 10 to the negative 5. So we are going to add up these. So this summation of these three will form our approximation. That'll give our approximation less than 10 to the negative 5. So we just have to add those three terms together and we are good. Let's get rid of that. So we have 0.35 divided by 12, and we'll put every term in front. 0.35 squared minus, let's get a denominator on that guy of 2. So we're just going to add these three together. And that'll be our approximation. right, any questions on that? So anytime we're doing calculus on a function, if it behooves us, we can replace the function with its power series and the math will work out fine. Let's do our last slide. So this is just sort of interesting. You can come up with all sorts of fun different representations of numbers. So the square root of e is a number. It's an irrational number. And if we wanted to come up with an infinite series representation of that number, we can just replace x in the power series for e with a half, because e to the half is the square root of e. So here is a power series representation of the number square root of e. We replace all these x's up here with a 1/2, so that's going to be a 1/4. So 1/4 multiplied by 2 factorial, which we could simplify if we care to. 1/2 to the 3 is 1/8, so we'll have 8 divided by 3 factorial, plus etc. So that is going to be an infinite series representation of e to the half. So anytime we have a power series, any individual value of x is just giving you an infinite series representation of that number. So this down here is no longer a power series though. Power series has an x, it has powers, it's a series of powers. This is just a regular infinite series of numbers. So this is chapter 10. So if we take a power series and we plug in an x value, we get back into chapter 10, which is an infinite series. And this infinite series converges because the interval of convergence here is all reals. So this infinite series of numbers will converge to that value. Similarly down here, if we wanted to come up with an infinite series representation of inverse sine of 1, we can use the power series for sine and just replace all the x's that we see with 1. And now we have an infinite series representation of the value sine of 1 radian. So that's more just of an observation and just trying to connect chapter 11 with chapter 10. So chapter 11, we have a function over here. Power series are functions. It's a function of x. We've got powers of x. Here is chapter 10, where we have an infinite series of numbers. So if we had this infinite series of numbers, we would be able to decide whether it converged or diverged, but we wouldn't necessarily know what it converged to. Like if we just were given this infinite series of numbers, we see that there's a factorial in the denominator. We could come up with the general term a sub n and then use the ratio test or the root test possibly, or whatever test works. So chapter 10, chapter 11. Make sense? All right, so let's go ahead and then hit our review. So the power series that you have to have memorized for this test are at the bottom here. So these are the 5. E to the x, sine x, GS is the geometric series, BS is the binomial series, and arctangent. Those are the ones. These two, ooh, that's not very transparent. The sine and inverse tangent, remember those are almost identical. The only difference is there's a factorial in the sine one, not in the inverse tangent one. All right, so let's start going through stuff, starting in chapter 10. So we'll go over to these questions and we'll just do as many as we possibly can. And I'll kind of pick some that seem like they might be on the exam. We won't have time to do them all. So let's start with the log limit one, because this I noticed on the worksheet. So the worksheets, I marked the ones that are right and wrong, go in and correct those and I'll close it Thursday night at midnight and then grade those things over the weekend. So, log limit process. Obviously, there's the shortcut here. You could say this is we should know by now that this converges to e to the 6. But on the exam, you'll have to show that work. You'll have to use that log limit process to show that it's e to the 6. So to do that, we are going to create an equation, take the log of both sides, take the limit of both sides, and work it out with L'Hopital's rule, typically. And so if we start, we can create this function, 1 plus 3 divided by x. You don't have to switch it to x's if you don't want to. You can leave it as n as you want. We usually switch to x conceptually because x is a continuous variable where n is usually thought of as a discrete variable. And if we take a derivative, you can't take the derivative of a discrete function. All right, so first, let's go ahead and take the natural log of both sides here. And when we take the natural log of the right-hand side, we're going to use that log rule that says powers can come down as multipliers. So we have that. And then we have to get the limit in there. So we take the limit of both sides. And when we take the limit of the left-hand side, we can push that limit inside the log function because the log function is a continuous function. And then on the right-hand side, we will have limit of all that. And let's combine two steps into one here. We know that we're going to go for L'Hopital's rule, and we've seen this pattern repeatedly. What we're going to do is shove that 2x into the denominator as the reciprocal of 2x. So this puts us in the form where we can, when we're taking our limit as x goes to infinity, we can apply L'Hopital's rule. Because in the denominator we get 0, and in the numerator we end up with natural log of 1, which is 0. So this is a 0 over 0 scenario. So L'Hopital's rule applies here. So we're going to reevaluate the limit after doing some L'Hopital. So I usually put a 0 over 0 here to indicate that we're going to use L'Hopital's rule. L'Hopital's rule says that the limit of a quotient of functions is the same as the limit of the quotient of derivatives. So if we replace each function with its best linear approximation, we will get the same exact limit. So what we have to do is differentiate the numerator and the denominator. So to differentiate that, the derivative of a log, we start with 1 over the inside. So the derivative of a log, 1 over the inside, multiplied by the derivative of the inside. So the derivative of this inside here is 0. Derivative of 1 is 0, plus this derivative. 3 over x is really 3x to the negative 1, so we end up with negative 3x to the negative 2, or negative 3 over x squared. So that's the derivative of the inside. Down in the denominator, we need to be a little careful here. It's 1 divided by 2x. So 1 divided by 2x, we would rewrite as x to the negative 1 over 2, or 1/2 x to the negative 1. So when you do this derivative, the minus comes down and you subtract 1. So this is going to be negative 1 over 2x squared. That'll be the derivative of 1 divided by the quantity 2x. So negative 1 divided by 2x squared. All right, so before we do any cancellation, let's just rewrite it once to make sure we're all on the same page. We'll flip that denominator and make it a multiplication in the numerator. So I would rewrite it like this. And if you rewrite it neatly like that, it becomes a little more obvious what's happening. We see that the x squareds are going to cancel. We see that the minus signs are going to cancel. And we are going to end up with the following. So we'll have the limit as x goes to infinity of, I'm seeing 6 divided by 1 plus 3 over x. And this limit is as x goes to infinity. And that limit is 6. And on the left-hand side, you still have this natural log of limit of y. And so we have to do one more thing. And that one more thing is to do what to both sides?
Exponentiate.
Exponentiate. So if we exponentiate, therefore, the limit of y, which is what our goal was, find the limit of that function y, is e to the 6. So that shows us why the limit of that is e to the 6. So this is a sequence. The sequence converges to e to the 6. If this was a series, if this was converted into this type of series, what would you say about this series?
That it diverges because it's greater than 1.
This is a divergent series
Nice.
because the limit of a sub n, or a sub k, is not 0. So the limit of this is e to the 6, so this diverges by a divergence test. So we just want to keep that distinction. So here we can have a sequence that converges, and that's going to correspond to a series that diverges. So the only way a series could converge is if the terms are going to 0. If the terms aren't going to 0, then it definitely diverges, which is the divergence test. Okay. I'm going to pass on that one. We've done a few of these. Did a bunch in your worksheet also, so hopefully that's enough for now. Let's just talk about these limits, make sure they make sense. So 0.2 to the n, the limit of this as n goes to infinity will be what? So as n goes to infinity, what's going to happen there?
It's gonna go to 0.
It's going to go to 0. Anytime we have a fraction, a proper fraction, a number that's between, it could be a negative proper fraction also, so -1 to 1, any fraction, any value there is going to go to 0 as n goes to infinity. So that's just the basic limit. So this will go to 0. It's going to oscillate depending on whether n is odd or even, but those positive and negatives are going to be converging onto 0. And then how about here? Limit of pi raised to the n as n goes to infinity. That limit will be infinity, because that pi is bigger than 1. So these are geometric sequences. When you take a constant and you start multiplying it by itself, you either go to 0 or infinity, depending on whether that constant is less than 1 in magnitude or greater than 1 in magnitude. Squeeze theorem. Let's just do one of these. So the squeeze theorem is kind of a generalization of what we just talked about. If the numerator is constant and the denominator is going to infinity, the fractions have to go to 0. Right? So this is kind of similar. Here, the numerator is not constant in either case. The numerator is not constant. The denominator is going to infinity. And the idea with the squeeze theorem is that, well, if the numerator is bounded, if the numerator isn't also going to infinity, if the fact was that both are going to infinity, we would go to L'Hopital. But if both aren't going to infinity, if the denominator is going to infinity and the top is just wobbling between two bounds, it's going to act as if it's constant in the numerator. That's the effect. But that's not proof though. The proof is that, okay, well, let's take a look at our bounded numerator. Our bounded numerator is, so truly it's less than that, but usually what we do is put a greater than or equal, or a less than or equal to symbol there, because you'll see in a second. So we know that arctangent is definitely between those two numbers. It's bounded between those numbers. And then we try to recreate the middle here. We try to recreate whatever this sequence is in the middle. So we're going to divide everything by 4 times n. So if we divide everything by 4 times n, I should have put an n, not an x right there. N. So we divide all sides, all pieces, all parts by 4 times n. So that middle one should be a 4 times n. So now we have that. Now the middle matches our sequence. Now we take the limit of everything. So when we take this limit, we do the limit across here as n goes to infinity. Limit as n goes to infinity here. Limit as n goes to infinity here. And of course, what we see is that the limits on the left and the right are both 0. So those are the traditional limits, the basic limit, tops constant, bottoms go into infinity, fractions go to 0. And so now we have that the limit of arctan n over 4n is sandwiched between 0 and 0, so therefore the limit is 0. So we put that less than or equal to instead of just less than, because here in the end, we want this to, you could leave off the equal to's, but it doesn't matter. Usually we stick them in. So therefore, the limit of arctan n over 4n is 0 as n goes to infinity. So the squeeze theorem just sort of justifies this intuition that if the denominator is going to infinity and the numerator is not constant, but it's essentially constant, it's just got a small range of values it takes on, the limit's still going to be 0. All right, so let's take a look. So the next slide is about recursive functions. And so this says find the first 4 terms of the following recursive sequence, and then find the limit of the sequence. So this sequence is going to start with -6. Whenever something's given to us recursively, we need to have a start value. And then the function creates our subsequent value. So what is the next value going to be? What's a sub 1 going to be?
Root 7?
So a sub 0 is -6, so we're going to
Root 8?
So we're going to plug -6 in right here, so we're going to have 6 minus 6.
Oh, okay, yeah.
So we'll get square root of 0, which is going to be 0. And then how about the next term? Square root of 6. And then the next term, square root of 6 plus square root of 6 inside. So that's what the first 4 terms are going to look like. Now, we don't know whether this sequence converges or diverges, but if it converges, and so to do the following step, we have to have some decent empirical evidence that it's going to converge. And so that decent empirical evidence would be look at a graph. So if we look at a graph, we could see pretty clearly whether it's probably going to diverge or probably going to converge. So if it's going to converge, here's how we find what it converges to. So this technique is a little bit of hand waving. We first have to at least have reasonable empirical evidence that it converges. So we're going to assume that the limit of a sub n is equal to whatever, L. Call it some number. So if we assume it converges because we've looked at the graph, then this will actually find L. So what we do then is take the limit of both sides of the definition up here. So we're going to take the limit of the left side, and we're going to take the limit of the right side, because our empirical evidence told us that it looks like it's going to converge. Well, the limit of these are now treated as two separate sequences. We think of the a sub n sequence and the a sub n plus 1 sequence as the same sequence, but missing the very first term. They have the same limit. So we get L equals the square root of 6 plus L. The limit jumps to the inside of the square root because the square root is continuous. And then we square both sides. And we have a quadratic. We know that to solve a nonlinear equation, everything goes to one side and you factor. And when you factor this, you end up with two potential solutions. But when you look at your sequence, the tail of it's all positive. So that limit cannot be a negative number. So we're going to rule out that negative. And this limit must be 3. That'll be the limit of that sequence. All right, let's go to the GS, one of the ones you have to have memorized, geometric series. Oh, this is still chapter 10 though. The geometric series you have to have memorized is really chapter 11. Although you still need it in chapter 10, but it's just numbers, there's not an X in it. You have an R instead of an X. So it's super important to be able to recognize geometric series and be efficient with finding your A and finding your R. So you know that for a geometric series, you've got this formula that S is equal to A divided by 1 minus R. You need to know that for your geometric series. Usually with a geometric series, we like to, if we can, think of it in this form. This is the most natural form for a geometric series. So you've got your first term is A, and then your common ratio is the R value. This is not written in that form yet. So we want to change this. We're going to rewrite this. And K is going to start at 0 here. This is going to be 1/9 quantity raised to the K. That is how we are going to rewrite that summand. Now we can see A and R. So this tells us that A is equal to what?
1.
1. 1/9 to the 0. So we use the initial K value to get A. So 1. And the common ratio? 1/9. It's whatever is below the K wrapped up in parentheses. And then we're going to compare that to 1. That's less than 1. So does this converge or diverge? Converge. So for a geometric series, if the common ratio is less than 1 in magnitude, it's going to converge. And if it converges, we then need to figure out what it converges to. So we now are going to use that S formula. So that S formula says that we have convergence, and it's going to equal 1 over 1 minus 1/9. So that's going to be 8/9 in the denominator, so it's going to converge to 9/8. That will be the sum of the series. Here's another one that's not quite in arc form. How are we going to rewrite that one?
8.
Close.
Oh, 16.
So The negative sign flips this to a 4, and then 4 squared is 16. So this is going to be 16 raised to the k power. K is going to start at 0. Okay, so again, let's identify A. Okay, it's 1 again. And how about the R value?
16.
16. We compare that to 1, and that is bigger than 1. Therefore, it's going to diverge, and there's nothing we can do. And so here's where you have to be careful. It's so tempting. So it diverges. If you blow this step here, notice that you can, there is an A and there is an R. You can plug the A in there and the R in here and get negative 15. Like, you can get this S, but that is not the sum of that series. This series diverges. So this is not legitimate. Right? You only plug in, that formula is only good if the common ratio is less than 1 in magnitude. Okay. This guy's geometric. You see an exponential top, exponential bottom. We need to somehow finagle it into the arc form. So first common mistake, is that minus affected by the power k minus 3? Is that minus included in the power?
No.
No, right? To include a sign, you would have to wrap the sign in parentheses in order to include it so that the power was affecting it. So this power has nothing to do with that minus. That minus is just sitting there. It's a minus 1 times 2 to the k minus 3. So that minus, if you wanted to, you could factor it all the way to the front. If you want, you could put it right there. That's totally fine. And then this inside part we're going to rewrite using laws of exponents so that we can strip away the exponents so that we can end up with just k. And it starts at 0 also. The traditional form of a geometric series is arc. So we have to get to arc. In other words, we need just a k in the exponent. And the rest of these constants can just factor out to the front. So we are going to have, for our series, we've got this negative 1 out front. This is going to be 1 over 2 to the 3. 2 to the 3 is an eighth. So that 8 is going into the denominator. We'll have 1 over 24 out in the denominator. 1 over 24 out in the front is a coefficient. So an eighth times a third. And then we have 2/3 to the k. So now we're in the arc format. So we can identify A, and A will be 1. We can identify R. R will be 2/3. And once we've identified R, we always compare it to 1. And if it's less than 1, we have convergence. If it's less than 1, we can figure out what the series converges to. Alexander?
Doesn't the negative 24 affect the A?
Yes. Well, it depends on how you think of it. If you think of this outside, what we'll do is find the sum of this and then multiply by negative 1 over 24. So you have the choice. It's just like factoring. You have the choice to factor a constant to the front or to leave it in. So we'll absolutely, when we find S, it has to come into play. So what we're going to say is that the sum of the series is going to be negative 1/24 multiplied by A over 1 minus R.
Oh, okay.
So we're going to treat that constant as a coefficient, if you will, to the whole series. So then we're going to come and do our A, which is 1 over 1 minus R, so 1 minus 2/3. 1 minus 2/3 is a third. Division by a third is multiplication by 3. So we end up with minus 1/8 as our total sum. GAS, geometric series. geometric series are exponential functions. Power is where the change is happening. The k is up in the exponent position. So geometric means exponential. All right, let's do a telescoping one. So this is a telescoping series. It's not obvious in the format that it's written in. What we have done to put this in the right format was to use PFD. When we factor this denominator, we see that we could break it apart. There's two linear factors, so we can break this apart into an a over k plus 1 and a b over k plus 3. And so we do our classic PFD thing. We multiply both sides by the left's denominator and cancel those corresponding factors on the right, which gives us our PFD equation. So that is our PFD equation. We had two basic techniques when we solved a PFD equation. Sometimes we use the convenient value method. Sometimes we use the traditional method. When everything is linear, the convenient value method is really a nice way to go. So let's go ahead and use the convenient value method. Those convenient values are the zeros of the denominators. When we plug in k equals -3 across the board here, oops, I didn't subtract right. So -3 is going in there, so we end up with -2. So this tells us that b is -1. Down here, we plug in -1 across the board. So we have 2a plus 0. So a is +1. All right, so that allows us to break that summand apart. So we're going to rewrite our summation as 1 over k plus 1 minus 1 over k plus 3. Now we're going to see that this is in fact a telescoping series. So when we're analyzing a telescoping series, what we need to do is look at S sub n. So S sub n always means the sum of the first n terms. So we have to add the first n terms together. So let's just start adding. We plug in 0, and we're going to get 1 minus 1/3. This is from n equals, or k equals 0, right? We're plugging in k equals 0. So these are our k values down below. I'm going to put the k values underneath. So this is the first term. Everyone agree? First term is corresponding to k equals 0. So that's S sub 1. So that's S sub 1. Now we go to A sub 1, the second term, plugging in k equals 1, and we get a half minus, so we're plugging in a 1 right there, so we get a half minus a fourth. So this is a k value of 1, that is the second term. Now we're going to plug in a k value of 2, and we're going to get a third minus a fifth. Third minus a fifth. This is k value of 2. This is the third term. Okay. Then we can put some plus dot 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 business in the middle. So there's going to be this stretch right there. And then we're going to add 2 more terms out here at the end. Tell me what the k values are going to be for these last 2 terms.
N minus one and N.
N minus 1 and N minus 2. It's always a mystery.
Okay.
If you have 5 fingers and you count from 0, 0, 1, 2, 3, 4,
Right.
right? If you start from 0 and you want 5, you have to end 1 less than what you're really looking for. Like if we want 5 terms and we're starting at 0, we would end at a counter of 4. So we want to end at n minus 1 because we started at 0. If we started at 1, we would end with k equals n, for sure. So this is the nth term, and this is the n minus first term. Okay, so let's plug in those numbers. We are plugging in n minus 2 here. So n minus 2, we're going to get 1 over n minus 1 minus 1 over, plugging in n minus 2 there, we get n plus 1. And then over here, we get 1 over, plugging in n minus 1 there, we get 1 over n minus 1 over n plus 2. So there is our S sub n. That is S sub n. Now we notice the telescoping business. So telescoping business, we see that the second part cancels with the first part after a skip. Second part cancels with the first part after a skip, so that's going to be somewhere in there. So as we're moving left to right, it's second parts that are canceling. So this is going to cancel with something that's in the muck in there. When we go from right to left, if we think about going from here left, when you're going right to left, it's the first part that cancels with the second part of the prior after a skip. So first parts are canceling. So when we go the other direction, this first part is going to cancel with a second part after a skip. This first part is going to cancel it with this n minus, if we plugged in k equals n minus 3, it would cancel right there. So the important thing is that there are going to be 1, 2, 3, 4 terms that are not canceling. So we can simplify S sub n to be 1 plus 1 half minus 1 over n minus 1 minus 1 over n plus 2. So that is S sub n.
Shouldn't it be N plus 1?
That should be an n plus 1. Thank you. Yes. Thank you. Yeah, that's the term that's preserved. That's the term that's preserved. So yes, pluses. And then S is going to equal the limit of S sub n as n goes to infinity. And so what will that limit be?
3 halves.
3 halves. 3 halves is what our limit will be. So that's how the telescopers work. All right, let's take a 10-minute break. And now we'll go call IT and say, hey, change the computer. But you didn't change.
I watched a lot of Breaking Bad back then,
Ah.
so.
I watched a lot of Breaking Bad. I guess I didn't absorb any of it.
I
would have had to learn through
You have to
osmosis.
lock in, you have to take notes.
Yeah, it's,
Take notes while you're watching Breaking Bad.
yeah.
No, I watched it when I was
You
young.
need to
Like,
channel
every
your
day when I came back
your
from
intervals.
class, before work, because I worked at the dining hall, it was a 5-minute walk, it was a sweet deal. I would watch Breaking Bad, I would get really, really high and watch Breaking Bad.
Walking Dead was my show.
That show, the first 6 seasons were so
They
good.
were so good, and then it just got like
Oh,
the
they're
same
fun.
thing
I
over and
know, it was so good.
Just gotta channel your inner Walter. Just gotta cook a
Channel
little bit.
Walter.
Then you ice it.
Oh, I was about to switch my degree to chemistry after I watched.
Because you could make so much
I
money?
got super high. I was like, I could do this. I could do this.
I know Jesse.
Maybe
Yeah.
Right?
Yeah.
Oh, Breaking Bad's motivated a lot of
It's like,
kids.
I'll minor in chemistry, so I have a fallback in case I fail as a
Exactly.
doctor.
You have a fallback.
Okay. Let me go make meth. Like, I can do that. I could do that.
Yeah, your mom would be proud.
She would be proud, actually.
Making money.
Oh, where's the world come to? All right, let's go with the DT, the divergence test. So remember, divergence test is not something we always write down, but it's something we should think about. The divergence test can never find convergence, but it finds egregious divergence. So egregious divergence is when the terms don't even go to zero. So like if we look at the harmonic series, we know that that diverges, but the terms do go to zero. So this is divergence. I wouldn't call this egregious, though, because the terms are, in fact, going to zero. But something that's egregious is like, oh, like 1 plus 1, that says 1 plus 1 plus 1 plus 1 plus 1. Right, that's egregious divergence. The terms aren't even going to zero. So it's not even in the ballpark of convergence. So that's the only thing that the divergence test can give us, is that type of divergence. And so even if we don't write it down, we at least think about it. Now here it says to use it, so let's actually do it, and not just think about it. So we want to take the limit as k goes to infinity of the a sub k expression. We want to take that limit. And clearly both the numerator and the denominator are going to infinity. And so we can use L'Hopital's rule. So this is an infinity over infinity scenario. L'Hopital's rule can be applied when you have 0 over 0 or infinity over infinity, both cases.
Can't you just use growth rates here?
You can use growth rates, but growth rates, we only use growth rates if we can't do it another way. Like if we can't do it definitively, then we say, oh, well, the denominator grows slower than the numerator or something like that. But we want to do it mathematically if we can. So this will be the limit of the quotient of derivatives. So in the numerator, we're going to end up with 1/2 k to the negative 1/2. In the denominator, we end up with 1 over k. Everyone agree on that denominator?
Yes.
1 over 2k times 2. Right, chain rule, 1 over 2k times 2. So the derivative of nk is always 1 over k. Derivative of natural log of nk, it's always going to be 1 over k, because you get the chain rule piece, 1 over 2k times 2. So we could write it that way if we want to just emphasize that it's going to be, come on. Why is that not erasing that 1.1? Oh my gosh. So 2 over 2k, and then those things cancel. Those 2's cancel. Okay, so when we do our simplification here, we end up with a multiplication by k in the numerator, and so we're going to end up with the limit of k, we'll still have the half out in front. So we'll have 1/2 k to the 1/2. All right, so this 1 divided by k turns into multiplication by k up here. K to the 1 times k to the negative half is that. This limit as k goes to infinity is infinity. This is super egregious. This is not equal to 0, therefore diverge by divergence test. All right, so that one must diverge. This one, same process. Like in our minds, we know that the limit of this is 0, but if we're asked to apply the divergence test, we've got to do some math. So we've got that. So there's a few ways that you can get at this. We've seen lots of different things. You can divide each term by the highest power of k. You could say, hey, the denominator is a polynomial, so it's going to be acting like its leading term. Its leading term is the dominant term. You could do a lot of things. The most common thing is to do that division by the highest power. So if we divide by k cubed across the board, we get this. So divide everything we see by k cubed. That's really multiplying by 1, which doesn't change the value, it just changes the look. And if we simplify that numerator, that's going to be 1 over k to the 5 halves, all divided by this. And what we notice is that these terms are going to 0 in the numerator, and this term right here is going to 0 in the denominator. So the numerator is going to 0 overall, and the denominator is going to 1 overall, and 0 divided by 1 is 0. So what do we say then about the divergence test in this case?
It's inconclusive.
Mm-hmm. So we say that that is inconclusive. Yeah. So divergence test, kind of a first test type thing to think about in your mind at least. Here we have a question that says, use the ratio test. Now, on the exam, I'm not going to ask you to find the pattern for a series, but let's do it in this case. The point I want you to understand here is that you need a sub n, or a sub k, depending on how they use their index. You need that in order to do the ratio or the root test. You need that a sub k so that you can then take the nth root of it or the kth root of it, or to do the a sub k plus 1 over a sub k. You need that. So let's just look at this one and see if we can figure out what the pattern is. In the denominator, I think it's pretty obvious that you have powers of 6. Right, that's 6 squared. 36 times 6 is 6 cubed. And then if you type it into your calculator, 6 to the 4th, 36 times 36 is going to give us that. So the denominator is a pretty easy pattern to see. And how about the numerator? Do we see any pattern in the numerator? Let's see. Anyone see anything? So we could come over and look at the factors of 32. 32 is 16 times 2. You could write this in lots of different ways. It's going to be 2 to the 5th, essentially. How about 243? Do we see any? And you notice anything about 243?
That's 3 to the 4th, isn't it?
Close.
Or,
3 to the 4th is 81.
Yeah, 3 to the 5th.
3 to the 5th.
Okay.
Right? That's 3 to the 5th. 3 to the 4th is 9 times 9, which is 81. So that's this. So all of a sudden we're like, oh, what are we hoping 1024 is?
4 to the 5th.
So somebody type that into your calculator and check. Is that 4 to the 5th? So 256 times 4. Yeah.
56 plus 12. Yep, it's 1024.
Right? We agree? So 4 squared is 16. 16 times 16 is 256. 256 times 4 is 1,000 plus 4 times 6, which is 1024. Okay, so it works. So our pattern we have then is, this one is, if you wanted to be super redundant, you could call that 1 to the 5th. And then this one we say is 2 to the 5th. This one is 3 to the 5th. This one is 4 to the 5th. So we see our pattern. So our a sub k is going to be, so if we this is 1, so a sub 1, we're going to call this a sub 1, a sub 2. You know, we don't have to start with 1, but in this case it makes the most sense. So a sub 1, a sub 2, a sub 3, a sub 4. And then we see pretty clearly that this is going to be whatever the k is, raised to the 5th power, divided by 6 to the k. All right. So use the ratio test to determine if this converges or diverges. So the ratio test says we are going to find r. Root test, they use rho. Ratio test, they use r. That's going to be equal to the limit of a sub k plus 1 over a sub k as k goes to infinity. And we're usually doing absolute value. Here it doesn't matter. Everything's positive. So we'll end up with lim of, let's see, that's going to be k plus 1 to the 5th divided by 6 to the k plus 1. And then we're dividing by a sub k, so we flip a sub k. Uh-oh. I'm having deja vu. And so our goal then, we have to simplify that rational expression. So we'll do a little crisscrossy thing. How many 6s are left over where?
1 in the denominator.
Everyone agree? Everyone see that there's 1 6 in the denominator? We can pull it to the front if we so desire. So those guys. And then the k plus 1 divided by k all gets raised to the 5th power. So we have that. We can write it like that. And what is the limit of that as k goes to infinity?
1.
Do you agree? Sure. 1?
No.
Or is
Yes.
it indeterminate?
No. Oh wait, it'd be 0. Because you can
What do
split
we
it
think?
into 1 plus. Oh, it'd be an e, wouldn't it?
I don't know.
Because you can split it up into 1 plus 1 over k.
So if it's an e thing, it's indeterminate. What is so 0 over 0 is indeterminate, infinity over infinity is indeterminate. What is the form, the indeterminate form for one of those e expressions? 1 to the infinity, is this a 1 to the infinity? 1 to the 5th.
1 to the 5th.
Is 1 to the 5th indeterminate? No. 1 to the 5th is 1 times 1 times 1 times 1 times 1, which is 1. Okay, so this is not indeterminate, so you do end up getting 1/6. Before we make our conclusion there, here's another way that we could have written it. So we could have said, we could have written this as 1/6 the limit of k plus 1 to the 5th over k to the 5th. So this way is going to be more obvious, but I wanted to write it that way because it's so tempting to think of that as an e. So tempting. But here you would write this as k to the 5th, and you could use your binomial theorem, and you would end up with this. Right? So you have polynomials of matching powers, and the limit at infinity for polynomials of matching powers is the quotient of coefficients, which is 1. So you would get, obviously, the same thing. But super important to recognize that this is not indeterminate. Right? That is not indeterminate. Indeterminate is when you have 1 to the infinity.
So if I had a k there.
Yes. So if there was a k there, then we'd be talking about e, if that was a k. Exactly. All right, so what is our conclusion then for the ratio test? Converge or diverge?
Converge.
So what do we compare this 1/6 to?
1.
1. So we compare it to 1, it's less than 1. So the ratio and the root test are identical to the geometric series when we talk about convergence. If that is less than 1, then we get convergence. So root, ratio, geometric series, less than 1, converge. Greater than 1, diverge. Equal to 1, indeterminate, inconclusive. Okay, so let's try a root test. So root test is usually, you at least try. When you see that the outer power is if you see that there's a power of k somewhere in there, the root test makes perfect sense to try. We have seen that sometimes the root test doesn't work and it's inconclusive, but we at least would always try that first, because if it works really well. So here we're going to take the kth root as k goes to infinity, so the kth root of all of this. And the root test would ask us to use the absolute value of the inside here, but there's nothing negative, so we don't even need it. So if we take the kth root of that a sub k, we're going to end up with the quantity k over k plus 5 raised to the 4k. 4k squared times 1 over k is just 4k. Now this one, is this one indeterminate? Right? So the base goes to 1, the exponent goes to infinity. So this is indeterminate. This is an indeterminate form. This one has that 1 to the infinity form. This has that e flavor to it. Now we can't, this question didn't ask us to use the log limit process, so we're allowed to use the shortcut. So the simplest way here is to rewrite the base by flipping it. And if you flip the base, you toggle the exponent. Flip and toggle. And then we can split the fraction in the base so that we have limit of 1 plus 5 divided by k to the negative 4k. Now it's in the proper form. And what are we going to get for that limit?
E to the negative 20.
E to the negative 20. So e to the negative 20, bless you. So what is our conclusion if we get e to the negative 20?
It's going to converge.
Do we agree? So this is a root test, which is the same as the ratio test, which is the same as the geometric series. If you get less than 1, and in the root test, I'll put it out here, they call it a row instead of an R. So if you get a row value less than 1, therefore we get convergence. So don't be lulled into the divergence test mentality. Divergence test says if the limit is not 0, it diverges. And remember what test you're using. So divergence test, if the limit's not 0, you say it diverges, but root, ratio, or geometric series, less than 1, converge. Let's go to a comparison test. So comparison test, when we look at this, the denominator has this subtraction in here, and we have the 4th root of k, which grows very slowly. It's a bird wing, 4th root of k. It's going to grow a lot slower than 5k. So the denominator here is really dominated by this 5k. And so if I'm told to use a comparison test, the first instinct is to create your b sub k by taking away insignificant pieces of this summand. The first piece that's certainly insignificant is this thing, is that 4th root of k, compared to what else is in the denominator. That's going to be insignificant. And so then we can choose our b sub k. The two choices are to just take it as is, or you could even say, oh, well, that 5 is insignificant as well. Multiplying by 5 isn't going to change, multiplying the denominator by 5 isn't going to change convergence or divergence. So you could choose either of those. What we have seen is that sometimes this one is more advantageous because when you set up the inequality for a comparison test, it's nice to match that. So let's choose this one. And when we choose that one, we are going to say this implies that the series 1 over 5 to the k, I'm just going to write out all the details just to be clear on this one. We have this. We don't need to indicate where it starts. All we care is whether it diverges or converges. We don't need a starting index value. And this is going to do what? Sum of 1 over k does what? So that diverges. It's the harmonic series. So this diverges, and you have to somehow tell me why. You know, if you do something like put in parentheses that it's harmonic, that's fine. We assume that we know that now. That's base knowledge. So it diverges because it's the harmonic. You could also say it's a p series and p is not greater than 1. P series converge when the p is greater than 1. The power in the denominator is bigger than 1. So our suspicion is that this series up here that we're analyzing does the same thing. That's our suspicion. So we would want to show that the a sub k is the one we're analyzing. A sub k is always the one that we, are looking at. That's a sub k. Do we want it less than b sub k or greater than b sub k?
Greater than.
Greater. So our basic concept is bigger than diverging diverges, smaller than converging converges. So if our b sub k is a divergent series, we're trying to show that the a sub k is even bigger because then it would also diverge. Bigger than diverging must diverge. That's what we would want to show. So, I don't even see where oh, there's the insert space over here. Can I just move that down? All right, that worked. So a sub k, we're going to put a sub k exactly as it's given to us. And we don't know, so we put a little question mark there. Then the b sub k that we chose is this. Now let's think for a minute in our head whether we, bless you, are going to be able to show this or not. Which of these denominators is smaller? The left denominator or the right denominator? Which denominator is smaller?
Left.
The left denominator is smaller because we've subtracted off something. Right, this is a 5k, this is a 5k minus something. So this denominator is smaller than this denominator, which means this fraction is bigger. Yeah, so we are going to be able to show it. But so usually the inequality thing is just confirming what we can tell. But we still have to do the math whenever possible. So we're going to cross multiply here. And when we cross multiply, we now see how important it was that we left the 5 in there. So when this 5k comes up to the top left, if this was just a k, we'd have a k here, and when we subtracted the 5k, we'd get negative 4k, and we'd have a hard comparison to make. But leaving the 5 in there makes it super simple, because these guys are just going to cancel each other out when we do our subtraction. And so we have 0 now on the left, less than or equal to a negative number. That is true. Everyone agree? 0 is bigger than any negative number. So, therefore, the series diverges. So then the original series diverges by the comparison test. So that was using the direct comparison test. Let's do an alternating series test. And typically if we can't make this work, we go to the other comparison test. So if this was a plus down there, we wouldn't be able to show that inequality, would not work out in our favor. So then we would go to the limit comparison test. Okay, oh, my box disappeared. So let's go ahead and let's do an AST. Let's do an alternating series. So it's asking us to use the alternating series test. Alternating series test has two parts. The first part is essentially the divergence test. So the first part says, take the limit of a sub k as k goes to infinity. And you have to remember that a sub k for an alternating series does not include the switch. That is a sub k for an alternating series. And so the limit that we're evaluating is the limit of 1 over k to the 3 halves as k goes to infinity. That is 0. So that denominator, k to the 3 halves, is a bird wing. It's going to infinity slowly, but it's going to infinity. 1 divided by something going to infinity will go to 0. So that checks out. That's the divergence test piece of that. If that's not 0, diverge by divergence test. That's not 0. And then the next piece of the alternating series test, we want to show that the a sub k's are decreasing. So we want to show that as we go further out, the terms are getting smaller. Sometimes you put an equal to here. It doesn't really matter. We already know the limit is 0, so it must be they must be going down. If it's not, I mean, if that limit is 0, for this next step to fail, take some work.
Are we able to use the p-series here, even though it's alternating?
No, we can't use p-series.
Okay.
So we can use p-series for the follow-up to this, which is whether we have conditional or absolute, if it converges.
Okay.
So we can't use p-series yet. Now in our mind, when we think about the alternating series test, if the terms are going to 0 and it's alternating, it's going to converge. So have this limit be 0 and this not be true, you would have to have some weird wiggly thing that would be very difficult for us to create. To create a decreasing function that's going to 0 but not decreasing, it would have to have some weird wobble in it, like built in. Still going to 0 but wobbling. It's super hard to construct, or not super, but harder than what we want to deal with. So when this limit is 0, the chances of this not being true are very small for all the functions that we use. Because to create those type of functions, you would need trig functions and weird arguments in the trig function. So here we have our a sub k, which is just 1 over k to the 3 halves. Here we have 1 over k plus 1 to the 3 halves. So that's what we want to show. Well, we first do our cross multiplication, of course. Let's get rid of the fractions. And then we can raise both sides to the 2/3 power. If everything's positive, you can take roots and raise powers. You don't have to worry about square rooting of a negative type business. So you can just erase the powers, because you can raise both sides to the 2/3 power. So we end up with that. And we can go one more. So we get that. This is true. So therefore, we have convergence by the alternating series test. So if the limit is 0 and the terms are decreasing in magnitude, definitely converges. So that is good. Now the question is, does this convergence rely on these minuses? Do we need the switch? Is that why this is converging? Like with the geometric series, which diverges, as soon as you put in a switch, it converges. So the alternating harmonic is conditional convergence. You have to have the minuses in there. It's conditional on the minuses. So now we ask ourselves, well, what role do the minuses play? Do they matter? And so we consider the series where we have no switch. So we start at 1 and we're just looking at this series. This series is a p-series. So this is where p-series come in. P-series don't have alternating signs. P-series have that form, 1 over k to the p. So that I know you know it's a p-series, you identify what p is. And then what do we compare p to? 1. We're always comparing to 1. So we compare it to 1. This is bigger than 1, which tells us converge or diverge.
Converge.
Mm-hmm. So therefore, do we have absolute convergence or do we have conditional convergence?
Absolutely.
It is absolute because the series of absolute values converges. When we take away the switch, what we are saying is that we're going to make everything positive, so we're looking at the series of absolute values. And if the series of absolute values converges, we call that absolute convergence. Absolute convergence. All right, let's take another look at this one. So this one's a little different, but first thing, it's an alternating series. Whenever we see that switch, alternating series, that means go use the alternating series test. Now, if you were in chapter 11 testing an endpoint and you came up with this, it's totally sufficient to do it in your head. When you look at this in chapter 11 as an endpoint classification, you would say, oh yeah, the limit of a sub k is 0, and it's alternating. That's enough. It's converging. In chapter 11, we don't give a hoot whether it's conditional or absolute. If we're just analyzing that, all we care about is does it converge or diverge. We don't care if it's absolute or, we don't have to do any sort of analysis without the switch. But here, where we want to do the full-blown AST, we first say, okay, well, what's the limit of a sub k as k goes to infinity? So that's the limit of 1 divided by k raised to the 3/2 power, 2/3 power. 2/3 power. That is 0, so that checks. So we know that the divergence test is inconclusive. And then we come down here and we want to show that the magnitudes are going down, which again is very hard for this not to be true. And you can put in the equal or not put in, it does not matter. So this technically would be showing non-increasing, which is what the theorem says. But in our experience, we can just replace non-increasing with decreasing. If it's not going up, in our experience, that means if it's not, so non-increasing means that it's trending down, but it could have some flat spots. But again, to create that would be very difficult, so you don't really need the equal to piece here. But regardless, we'll just leave it this time. Does not matter which way you go. So 1 over k to the 2/3 is that greater than or equal to 1 over k plus 1 to the 2/3. We're pretty sure it is. We do our cross multiplication. Everything is positive here, so we can do whatever power or root we want to both sides. So we get k plus 1 greater than or equal to k. Yeah, that's true. True. So that checks. So therefore, we have convergence of the alternating series. So the alternating series converges. All right. Whenever we have an alternating series that converges, we can then ask whether that convergence is conditional or absolute. So to analyze that, to know whether it's conditional or absolute, we consider the series of absolute values. So if we look at the series of absolute values, that's the series of absolute values. So the series of absolute values, we just take away the switch. This we recognize instantly as a p-series. We identify p. We compare it to 1 and make a conclusion. So does this series converge or diverge?
Diverge.
So this series has a p-value less than 1, so therefore it diverges. And our big conclusion is that the original series, which it's kind of, you can say it, it's kind of hard to, the original converges or diverges. Or no, I'm sorry. The original converges conditionally or absolutely?
Conditional.
Conditionally. Yes. So it's going to converge conditionally because the series of absolute values diverges. Just like the alternating harmonic, you need the minuses in order to get that convergence. So the minuses are necessary. IOC. The most important part of chapter 11 really is being able to find an IOC. So let's take a look at this first one. So to find an IOC, we are going to use the ratio test or the root test. Either one will work. This one looks like the root test would be a nice way to go. You can do either, does not matter. So we'll call it rho if we're going to do the root test. So we're going to take the limit as k goes to infinity of the kth root of a sub k. And we take an absolute value for this. So it's going to be absolute value 8. And here we do need the absolute value because that absolute value is, we have an x in there. And x could be negative. X is just some number. We don't know if it's positive, negative, whatever. So we definitely, when we push the absolute value down, we need to keep it around the x. Everything else is positive, but the x might not be. So the kth root of a sub k, we're going to end up with 8k absolute value of x. Because the kth root of that k power, those vanish. They annihilate each other. Now everything that doesn't have a k can jump to the front of that limit symbol. So we can make this 8 absolute x limit of k. Right. Anything that's not a k is constant with regard to k, so it can factor to the front of the limit. And then this limit is as k goes to infinity, so what does that limit equal? Infinity. So, therefore, what is the radius of convergence, and therefore, what is the interval of convergence?
Infinity and then infinity to infinity.
So,
Oh, wait, no, it's 0.
backwards,
Right, 0.
because when we do a root or a ratio, we compare to 1, and convergence is when that limit is less than 1. Right, so if we do a root test, which is with the rho, a ratio test, which was with the r, at the end, once we get that limit value, we compare it to 1. Less than 1 converges for geometric series, for ratio test, for root test. Is that ever less than 1? No. So the radius of convergence is in fact 0, and the interval of convergence is really a degenerate interval. It only contains a single number, and that single number is the center of the series. And what is the center of this series?
8x.
Center of a series is always a number. What would the center of this series be? When in doubt, it's 0. Do you see x minus 2 or x plus 3 or, right? You don't see any horizontal shifting. So if there's no horizontal shifting, like an x plus 4 in parentheses, an x minus 7 in parentheses, this is an x minus 0 in parentheses if you wanted to. So the interval of convergence is only going to contain its center. Super boring series. Every series converges at its center. That one only converges at its center, so not a very interesting series. Now this one, we're definitely going ratio test because we see that factorial. Most of the series in chapter 11 we go with the ratio test. Most of the time. We're going to go ratio test. The only time we don't is if there's a really explicit power of k out there. So we are going to take the limit as k goes to infinity of the absolute value of a sub k plus 1 over absolute value of a sub k. That's the ratio test. The ratio of consecutive terms. So, limit a sub k plus 1, we replace the k with k plus 1, take the absolute value we don't need an absolute value in the denominator on that k plus 1 factorial. So that is a sub k plus 1. Absolute value must be present because we have an x. X is any real number at this point. Dividing by a sub k is the same as multiplication by its reciprocal. So we have that. All right. Well, let's look at the let's look at the factorial ones first. What's going to happen with the k factorial and the k plus 1? What are we going to be left with and where?
K plus 1 denominator.
Yep, k plus 1 in the denominator. Everyone see that? Because k plus 1 factorial is k plus 1 multiplied by k factorial. Okay, now let's look at the 2 thing. Is it clear that these 2's just cancel? It's all multiplication, so that's a common factor. And now let's look at the x's. Oh, 1 extra x up top. So we're going to end up with absolute value of x in the numerator. All right. Anything that doesn't have a k in it can come to the front. So we have absolute value of x times limit of 1 over k plus 1. And what is that limit as k goes to infinity?
0.
0. So what is the radius of convergence? Whoops. What is the interval of convergence? Let's see. What about the radius of convergence? So we're comparing this to 1.
Is this, that'd be all real numbers?
All real numbers.
It's true for
Because
all.
that limit is 0. So it doesn't matter what x is, that limit is always 0, which is always less than 1. Less than 1 dictates convergence. So this means it's converging no matter what x you plug in. So the radius of convergence we say is infinite, and the interval of convergence will be all real numbers. So this is the other extreme case. Converges for everything. These are the 2 cases that are great, as long as you don't get confused and switch them around, because you don't have to test the endpoints. So that's what's great about the 2 extreme cases. Now, the pain in the neck case, where you have to test endpoints, we've got this thing. Let's go with the ratio test because we see a bunch of stuff up here. It's not a clear root, so let's definitely go with the ratio test. So that's going to be an r equals limit absolute a sub k plus 1 over absolute a sub k. Limit. So absolute k plus 1, we just replace all the k's with k plus 1. Take the absolute value of the part that has an x in it. So this is going to be 5 to the k plus 1 minus 1. So that's just 5 to the k. Up here, be super careful. We're replacing that k with k plus 1. So that's going to be 2k plus 2 plus 1, which is 2k plus 3. So just be careful there. So that's x to the 2k plus 3. And then multiplying by the reciprocal of absolute a sub k, we're going to end up with a 5 to the k less 1 up there. And in the denominator, we're going to have absolute value x to the 2k plus 1. All right, so looks like we have 1 extra 5 down below. Okay, so we can pull that 1/5 to the front if we like. There's no reason not to get it out of the way. How many more x's do we have in the numerator?
2.
2. Everyone agree? 2k plus 3 is 2 more than 2k plus 1. So we have 2 x's in the numerator. we don't need the absolute value around an x squared. X squared is always positive or non-negative. So we have that. So what is the limit of this as k goes to infinity?
X squared over 5.
Yeah, there's no k in there. So the x squared and the 1/5 are both constant with respect to k. So that limit is, the limit of a constant is itself. So this is going to be x to the 2 divided by 5. That is the limit. Now anytime we do a root or a ratio test, we compare to 1. And this is what we see about a power series. Some x's are going to give us ratios less than 1, and some x's aren't. Right? So it depends on x. So this says that x squared has to be less than 5. And if you write this as a compound inequality, you would say, you would have this. Let me do one other thing first, just to, so let me do one other thing first. If you took the square root of both sides here, when you look at that, both sides of that are non-negative, and when you have non-negative stuff going on, you can take whatever roots you want. So if we were to take the square root of both sides here, what is the square root of x squared?
Absolute X.
Absolute x. And so what we're thinking then is this. And we don't know about the endpoints yet, but that's what's kind of where we're at. So at this stage right here, when we have that, you can say this for sure, but this is kind of a cleaner way to get at it. That just works really nicely if you just take the square root there, and then you get your absolute value of x, and you're good. So what is the radius of convergence?
Root 5.
Everyone agree? So if you look here, the center is 0. We're going root 5 to the right, root 5 to the left. So the radius of convergence is definitely root 5. And you can see the radius of convergence. You can't see it here. You have to isolate the x before you can see the radius of convergence. So here it's a little easier to look there. Now we don't know about these endpoints. The IOC, we don't know about the IOC. The IOC, we know that the left endpoint is negative root 5. We know the right endpoint is root 5. But we don't know about these endpoints yet. Right? We got to test those. We don't know. So we know that we have convergence between those two endpoints, but we don't know about at the endpoints. So we've got to do a little bit of work. So we're going to test x equals negative root 5, and we're going to test x equals positive root 5 to figure out what's going on at the endpoints. So we come back to the original series, and we replace that x with negative root 5. So series negative root 5 to the 2k plus 1. So negative root 5, and that whole quantity is raised to the 2k plus 1, divided by 5 to the k minus 1. And down here, let's just write it while we're sort of doing the same type of thing. This one is going to be a root 5 with no negative to the 2k plus 1 over 5 to the k minus 1. All right, so we're going to analyze both of these series. The first thing we're going to do up here is peel out that switch, or the thing that looks like it might be a switch. Maybe it's not a switch. We'll ask that question right now. So we're going to get rid of that, and then we have square root. Well, let's talk about this. Everybody follow that? The minus 1 comes out. We're distributing that exponent. So first off, is that a switch, or is that not really a switch? What is the parity of the power when you plug in k equals 0, odd or even?
It'd be odd, right?
If you plug in k equals 0, you get a power of 1, which is odd. If you plug in k equals 1, what's the power? odd. Plug in k equals 2, it's odd, right? So 2k is always even. And if you add 1 to an even, you get an odd. So this really is not a switch. This really is equal to -1. It's always -1, right? If the power is always odd, an odd power on -1 is -1. So that thing is not changing from -1 to +1. It's just -1 on all the time. So that's really not a switch. Okay, now let's look at this square root of 5. We see a 5 in the denominator. We see this 5 buried in this square root here. We want to mash those together at some point. We want to combine those 5s. So I'm going to think of this in the numerator as 5 to the 1/2 raised to the 2k plus 1. So 5 to the 1/2 raised to the 2k plus 1, we have to multiply the 1/2 times 2k plus 1. So if we rewrite it, that's going to be 5 to the 1/2 times 2k is k plus 1/2. That's going to be the numerator. And the denominator, we have 5 to the k minus 1. So that's where we're at. Then we figured out that that's not really a switch, it's a minus, so let's just pull it to the front. What do we have left in here? We have two exponential expressions. They have the same base. So we can subtract the exponents. So we're going to have k plus 1/2 minus k minus 1 in parentheses. All right, so this exponent minus that exponent, k minus k, bye-bye. 1/2 minus minus 1, 3/2. So this is what we end up with. The k's are gone. So does that series converge or diverge? Yeah, one or the other. Think about what the series looks like. There's no k in it. So you're just adding the same thing again and again and again and again. So when k is 1, you have a 5 to the 3/2. When k is 2, you have a 5 to the 3/2. When k is 3, you have a 5 to the 3/2. So does that converge? No. If you add the same non-zero number to itself again and again and again and again, it diverges. The only time you can add a number to itself and not get divergence is if you're adding 0. If you add 0 plus 0 plus 0 plus 0. But here, you're adding. So you could also say to yourself, oh, that's a constant. I'm going to bring it out to the front. That's not going to change convergence or divergence. So if you factor out that 5 to the 3/2, what's left inside? 1. So the reduced series is really 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. That diverges, and if you multiply it by a constant, that's not going to change it. So we would say that this diverges by divergence test. Because the limited base of k is not 0. All right, so that means that we are going to exclude the left endpoint, so we put a parenthesis right there on the left endpoint. Now let's test the right endpoint. All right, there's no negative sign to deal with here, so that makes some of our analysis a little easier. There's no switch. But we're going to do that same type of thing. In the denominator, we have 5 to the k minus 1. In the numerator, we need to turn this into a base of 5 instead of a base of square root 5. So that power of 1/2 gets distributed to the exponent. We multiply them together. So same idea. We're going to end up with k plus 1/2. So that's looking really familiar. Then we combine our exponents. Combine these exponents. And we have 5 to the, subtract off the denominator. So k minus k is 0. 1/2 minus minus 1 is 5 to the 3/2. If you want to, you can factor that out to the front. And when you factor that out, you have that. Diverges by divergence that diverges by divergence test. So our IOC is open on both sides. There is our conclusion. So when we don't have those two extreme cases, we've got extreme work to do. We've got to test the endpoints. Okay, let's take a look at the hardest question on the test, is always this one. So let's go make sure we take a look at this. This is always the most challenging question. So find the power series representation for G, centered at 0, by differentiating or integrating the power series for F. So we're starting with F. We need to build a little map on how to get to G from F. All right, so how are we going to get to G from F? So it says either integrating or differentiating. What do you think? Is that a derivative? Is that an integral? How do we get to G from F?
Is it a derivative?
Looks like a derivative because the power in the denominator is increasing. And we know that if we had 1 over x and we differentiated it, we'd get negative 1 over x squared. The power would go up if we differentiated. So let's check. Let's take a look at the derivative of f and see what we get. So f prime of x, and it's probably easiest to write this as 1 plus, we can just use the quotient rule. We can use the quotient rule. We're adults. Low d high is 0. Minus high d low. So negative 10x is the numerator. So that's low d high minus high d low over low squared. Ooh, yeah, we're almost there already. Okay. Now, G only has an x. So what I'm going to do is divide both sides by negative 10. So if we divide both sides by negative 10, now we have G. So G, the roadmap, is that we take F, find its derivative, divide by negative 10. That is how we build the power series for G from the power series for F. So that's our roadmap right there. That tells us how to get to a power series for G. Now, that means we need to find the power series for F first and foremost. All right, so this should remind you of an alternating geometric series. So we know that the geometric series, 1 over 1 minus x, is the summation from 0 to infinity of x to the k, and that the interval of convergence is negative 1 to 1. So that's the geometric series. The alternating geometric series, we would replace the x with negative x, and if we replace the x with negative x, we're going to end up with a negative 1 to the k times x to the k. And this interval of convergence we've seen does not change in this case. So there's the alternating. Now we're almost to F. What are we going to replace x with to get to F? The x becomes? What's your hunch? You can say it out loud.
Probably 5x squared?
Yeah, 5x squared. So if we look at this, the only difference is that we need to turn this x into a 5x squared, which means we also have to turn that x into a 5x squared. So we've got our 1 plus 5x squared in here. Now we have what we're looking for. This still starts at 0. We have to come over here, replace this x with 5x squared. And then we'll have to do a little math on the interval of convergence. The interval of convergence will be negative 1, 5x squared, 1. So if you do a substitution, you always have to also substitute into the IOC. So then in here, let's clean this up a skosh. We're going to have negative 1 to the k. This will be a 5 to the k multiplied by an x to the 2k. This will be a negative 1/5 less than x squared less than 1 over 5. X squared is always bigger than negative 1/5, so you can use our shortcut algebra technique to just say, oh, well, it's just that, right? X squared is non-negative, it's always bigger than any negative number. And now if you apply the square root, everything's positive or non-negative there, so you can take roots. Well, the root on the left is absolute x less than 1 over the square root of 5. And so this is the new interval of convergence. If we take away that absolute value, is going to be this interval. That's our new IOC. Don't have to test endpoints there, because all we did was a substitution. Okay, so now the function g, we need f prime. So let's come over here and find f prime. So f prime of x, negative 1 to the k, that's a constant. 5 to the k, that's a constant. When you take a derivative, constants just drift. And then in here, we're going to have to bring down the power and then subtract 1. And when we do that, when we take a derivative of a power series, we have to check our index, because our index could change. K equals 0 is going to give us an x to the negative 1, which is not a polynomial. If we start at k equals 1, then we get a 2 minus 1, which is 1. That's legitimate. So there is our power series for f prime. So the power series for g is going to be that power series multiplied by 1 over negative 10. So the power series for g is negative 1/10 this. I'll write that cleaner in a second. But that's the power series. And the last thing we would have to do is test the endpoints. I'll test the endpoints as you are walking off into that world out there. So we have to test endpoints whenever we use, so we didn't test endpoints over here because that was just a substitution. But as soon as we take f prime, that's where the interval of convergence is going to change, as soon as we take a derivative. So then we just have to test the two endpoints, that one and that one. We'll test those.
And we plug that into G,
So we're going to plug that in to right here.
the F prime.
So the f prime, this is where the IOC is changing. So before we take the derivative, it's just substitution, nothing changes, so then that's going to change once we take the derivative. I'll clean that up a little bit and write it neatly so that you can follow it. All right, so between now and Thursday, look at the ones that we didn't do. I will try to write out solutions for each of them. I don't know if I'll be able to get to all of them, but if you are looking at one of them, you aren't seeing the solution, just email me. I check my email all the time. I will write it up and send it to you. If there's one of those you're not sure about. Good luck studying. Final midterm.